flux phi. Remember we had phi E with electric flux. Magnetic flux is the same idea. Phi sub B is B A cosine theta. So you need a magnetic field. It's in some area, and there's an angle between the field and the area vector. Okay? Faraday's law says that the average induced EMF in a loop or in a coil is going to be minus delta phi B, it's a phi, B delta T. You need flux, magnetic flux, and it needs to be changing, and if it is changing, you get an induced EMF, meaning you can make a current. You can push current around a circuit. The negative is there because the induced current will always oppose the change. So in some places you won't see people put the negative in, but I think our text has the negative, okay? So here's a coil, and here's a little, it's called a galvanometer, so it's a pretty sensitive little ammeter. And if I move this magnet into the coil, you can see that I get some induced EMF. I get current being made. Okay, this is how generators work. You have a changing flux in a coil. You get current, okay, or an EMF. All right. The faster I change it, the larger the induced EMF. Change it very slowly, I get a small induced current. Okay. Yeah. Same thing here. That would be, if I looked at this case, that would be B is changing. The area is not changing. The angle between the field and that area is not changing. Okay, let's pretend we've got a constant magnetic field. So that area is not changing and this angle is not changing. Here is a little hand generator, and it's got a permanent magnet inside here, and there's a coil in here, just a copper coil, and as I turn it, I can generate power. Faster I turn it, all right. Hopefully that makes sense. You put more energy in, you get more energy out, or power. And so the faster I'm turning it, I'm decreasing delta T and making this larger. Okay, I'm powering the bulb with that loop moving through the magnetic field. So everything we saw previously was like a charge moving into a constant field. Okay, but as long as you have this relative motion between the loop and the field, you get an induced EMF, all right? Doesn't matter if I move the magnet into the loop or the loop toward the magnet. It seems kind of silly, but that was Einstein's problem. It's one of the ways he thought about special relativity. What's the difference in moving the magnet toward the loop or the loop toward the magnet? There is none, okay? So what I want to look at today is based on this idea is induction or self-induction. Okay, I'm just going to call it induction. Induction and inductance. Okay. So let's imagine that we have a solenoid. We all know what a solenoid is now, just a tube. It's wrapped. It's got a bunch of tightly wound turns on it. I'm not going to draw them tightly wound, but okay, something like this. Lots and lots of turns. And here's, oops, I don't want to go through it. Here's the last one. Okay. And I connect it to a power supply and a switch. Let me draw this. Here's my switch. Okay. Well, when I close the switch, so boom, close the switch. What's going to happen? You're going to get a current in the coil. We already know that. It's a continuous coil, but you're also going to get a magnetic field from what we know about coils and magnetic fields. There's going to be a magnetic field produced due to that current. And that magnetic field in a solenoid is, okay, if the current's that way, it's going to be this way. Let's see. Okay, let's say it's that way. You get a changing magnetic field inside a coil due to the fact that you're putting a current through the coil. So this coil or this solenoid reacts to its own magnetic field. Okay? Doesn't matter where the magnetic field came from, it doesn't know. And Faraday's law says, well, if you have a changing magnetic field in a coil or in a loop, you get an induced EMF. So it reacts, this is called self-induction. It reacts to its own magnetic field because of the way it's shaped. All right? It's a coil. It's a tightly wound solenoid. Because of that shape, you get an induced EMF due to Faraday's law. Faraday's law says a changing magnetic field gives you an induced EMF, and the inductance, okay, so E sub L, this sometimes called back EMF, or the voltage that's produced across the coil, is equal to minus L di dt. So you need the current to be changing. You have to have the current changing because by Faraday's law, that flux needs to be changing, that magnetic field. And this is called the inductance. The inductance sort of plays the role like capacitance, right? We had a capacitance based on a changing voltage. We close the switch and the capacitor charges in a certain amount of time due to the capacitance, okay? In this case, we're going to see that this induced EMF changes in time due to the inductance of the coil. The inductance has units. Anybody know the units of inductance? Happen to know? No. It's called a Henry. A Henry. Right? Units of inductance are Henrys. A Henry is a volt second per amp. Okay, it's a volt second per amp. It's capital H. So when you see that SI symbol H, that's Henrys. Capital H is Henrys. Okay? So that voltage appears, okay, it appears across here. I'm going to say this would be E sub L. All right, so if you were to measure that induced EMF, okay, in the coil, you would measure it there across the whole thing. All right. So I'm going to combine, I know we haven't really talked with you guys about Faraday's law, but I'm going to combine what I talked about with Faraday's law with this induced EMF, this back EMF. So in d phi B dt, this is Faraday's law. Okay. That's from Faraday, just the number of turns times the change in flux with respect to time is equal to L di dt. Okay, and that came from what we did with inductance here. You can get rid of the dt's, and in d phi b is equal to L di. Integrate, and you get n phi b divided by I is equal to L. Now, how useful this is, I'm not sure. I may do some simple problems based on this. But it just says that if you know the flux and the current and the number of turns, that gives you the inductance. Okay. So I want to calculate the inductance for a solenoid, like I've got up here. Okay. All right, so for a solenoid. And we'll see that this inductance is just a function of the geometry, the number of turns, and all those things. Just like with a capacitor, the capacitance ends up being just a function of the area of the plates, the distance between the plates, you insert a dielectric, whatever it is. It's the same kind of thing here. It has to do with how the coil is made. So we know for a solenoid, the magnetic field is equal to mu naught capital N over L times I. Remember that? If you have a current in a solenoid of N turns and length L, that's the field. You multiply that by mu naught and you get the field. So the flux, phi B, so recall for a solenoid, this would be the length L, and this has some area A, and there's a magnetic field inside here. It's nice and constant, it's uniform, okay? That's inside the solenoid. Then the flux would just be BA. Magnetic flux is just like electric flux. It's that field strength times an area. Okay. So the flux would be BA. So I'll put that in here. I'll put this in here. So this is equal to, from what we did up here, mu naught N over L I A. Okay. Now, I'm going to equate that to L. I'm going to equate that to this. Okay, L, the inductance, is equal to N phi B divided by I. So this is equal to mu naught N over L I A. Then I have to multiply by N over I. That cancels, and you get an N squared. So for a solenoid, the inductance of a solenoid, L sol, is equal to mu naught N squared over L A. Okay. So the inductance goes like the square of the number of turns. So it just depends on the length of the solenoid, the area, that cross-sectional area of the solenoid, and the number of turns. Okay. So let us calculate, just to get a feel for how a reasonable solenoid, I guess we could use this one. Earlier I did something different, but okay. All right, so here's my solenoid. It tells me on here that this thing has 500 turns. Boy, it looks like more than 500 to me, but maybe not. Yeah, maybe that's about 100. 2, 3, 4, okay. All right, so N is equal to 500. The length, I shall now measure it. I don't know if it goes all the way to that, but doesn't really matter. 60 centimeters, so 0.6 meters. Area, let me measure the diameter. I'll write that out. Diameter is equal to I'm going to say about 8 centimeters. Diameter is 8 centimeters. What else do I need? That's it. I don't even know if this old thing still works, but it probably does.
So in real life, the solenoids always stand erect or
Oh, they can be anyway, yeah. Okay, so let's calculate. The inductance is equal to mu naught 4 pi times 10 to the negative 7 Tesla meter per amp times 500 squared. That's the total number of turns. Times the area, well, that's pi times the radius squared. 0.04 meters squared divided by the length, 0.6 meters. Can somebody please calculate this? I have no idea what the answer is. I'm guessing it's something in the millihenry range, but yeah, millihenries. It's too much.
0.026319.
26.3 millihenries. Anybody else get that, or nobody else tried? We'll go with that. It sounds reasonable. I'm thinking it's something in the millihenry range. Okay, so 26.3 millihenries. This coil, I know, is about 0.9 henries, so it's it's got a pretty big inductance. It's as compared to this. This thing has 3,600 turns, 3,400 turns though. So you take N equal to 3,400, that's going to be much larger inductance. However, this is not a solenoid. It's not much longer than it is round. Okay, all right. 26.3. So I think that's on the equation sheet. It should be. Not a big deal, but. So let's see how an inductor will work in a circuit. So I'll look at the RL circuit. The RL circuit. So in lab, we had the RC circuit. This is the RL circuit, meaning it's an inductor and a resistor. Well, here's the power supply. Here's a resistor. Inductors are usually drawn as little coils like that. And down here is a switch. So here's L and R, plus minus, that's an EMF. Power supply. So what did we find when we charged the capacitor? I know that we did the discharge, but when you charge a capacitor, it doesn't charge instantaneously. You close the circuit and it starts charging depending on the size of the capacitor and the resistance that's present in the circuit. And we saw that equation that depended on 1 over RC. That was tau. The time constant was RC. This is the same kind of thing. When you close this circuit, current starts to flow in this direction. Doesn't really matter. Current starts to flow in this direction, but you get an induced EMF here because you have a changing field in this inductor. It has some inductance, okay? So that's sometimes called a back EMF. Like I said, you get a resistance to current flow due to that changing field in the inductor. So if you go around this circuit and you add up, you get E minus IR, I think it's minus L DI dt. Remember, that's E sub L, okay? That's the voltage across the inductor. That's the voltage across the capacitor. That's the voltage from the power supply. Solve this. I'm not going to go through all the math. I'm sure you're disappointed about that. Let me just, what did I do with that? Here we go. Okay. So you get the current, I'm solving for the current. The current is equal to E over R times 1 minus E to the minus R over L T. That's, that is after you close, well, let's look at it this way. At T equals 0, I close the switch. What is the current at T equals 0? Not a difficult question. What? 0, yes. This is 1. Okay? You get, that makes perfect sense, I hope. The current doesn't instantaneously, all right, that's what I'm talking about. You get a rapidly changing current. Okay, the change is great, but it does start out at 0. What happens when T gets very large? Now those of you who said something different than 0 previously. What happens as T gets large? What happens to an exponential that has a negative exponent. It goes to 0. Yeah, this goes to 0. So for large T, the current just goes to E over R. It just goes to the voltage divided by the resistance. So you get a constant current in an RL circuit, and there is a magnetic field in this inductor, and there's energy stored in the inductor. What happened with the capacitor? With the capacitor, you got this voltage that started out at boom. When you close the circuit, the voltage went boom, and then the voltage across the capacitor built up, built up, built up. That was all stopped. There was no more voltage, and you got energy stored in the electric field. In this case, you go to a constant current, and the energy is stored in the magnetic field. All right? So if I plot current versus time, it looks something like this. And it approaches, that is E over R. Okay? It has an asymptote at E over R. Okay? For the mathematicians, it never actually reaches E over, no, it does. All right. So this is what the current looks like. T equals 0, it's 0. You're closing that switch, current builds up, builds up. What happens when I open the switch? Anybody happen to know? Well, the nice thing about the capacitor is when you take the capacitor out of the circuit, the way it's constructed and the way nature makes it, you got this nice steady electric field in between the plates, if we're thinking about a simple capacitor. And you can take that energy around, but when you stop current flow in an inductor, the field collapses. You have no more field. There's no current flowing. So you collapse the field very rapidly. That's a quickly changing field in a coil, and you get a spark usually. You get a large induced EMF. Have you ever been running like a vacuum cleaner or a motor and you unplug it and you see the spark jump from the receptacle to the little plug? Okay, sometimes you see it when you plug it in, but oftentimes it's running and you see, okay? That's what's happening. You have an inductive load and you have energy stored in the magnetic field due to the current, and as soon as you turn off that current, that energy has to go somewhere. Okay, and it usually induces a large EMF and you get a spark. All right. That's why on computers and so forth you have surge suppressors, because inductive loads that turn on and off all the time, you get these spikes. You get these induced EMFs that are large that can travel through the circuit and destroy things. Okay. A device that uses this idea, and this is really Faraday's law, this is not an RL circuit, but is a magneto. Nothing to do with X-Men. Okay. These magnetos were around a long time before Magneto from X-Men. This is like I think it was a blower or a weed eater. It's probably a blower. And you have a spark plug. So this is what's igniting the fuel. You have a cylinder. Okay, take my thermal physics class and we'll talk all about engines. You have a cylinder and a spark plug. So you need a spark to ignite the fuel. This little thing called a magneto is really, it's a simple little coil that has an iron core. And so here's a coil. It has this little iron core. And that coil makes a circuit with the body of the engine and the wire that goes up there to the spark plug. And what you do is you bring a magnet in front of that coil very, very quickly, and you change the flux in that coil really, really fast, and you get a large induced EMF, and it makes a spark. And so in the little, this is called the flywheel. So in the flywheel, there is embedded a magnet. And as that magnet goes by the magneto, okay, you're changing the flux in that coil really quickly and making a spark. So when you're pulling that cord, you're making that magnet fly by the magneto, and you're inducing a spark, and you're also, doing a lot of other stuff. Let me show you that. I think I've got something here. My keys, all these keys. All right, this is definitely a magnet. All right. And the faster you turn it, the larger the spark. Okay, and if any of you have experience with cranking blowers and weed eaters and mowers like I have my whole life, they can be really annoying. So, oh, by the way, I did want to mention on this, look at this term e to the minus r over lt. Back to the stuff we did with capacitors, L over R, the time constant, in this case, for an RL circuit is tau is equal to L over R. L over R has units of seconds. Okay. For the RC circuit, it was RC had units of seconds. L over R has units of seconds here. Okay. So let's look at an example based on this. I'll get rid of this. Let's say that we had our inductor. What was it? Let's let L equal 20, we'll make it simple. 26 millihenries. Let's let R equal a kilo ohm, 1 k ohm. Okay. The question is, let's say I close the circuit. How long? So this is an RL circuit I'm talking about in this equation. How long does it take for the current to reach 1/2 its maximum value? Okay. So I've got an RL circuit. The inductor is 26 millihenries. The resistor is a kilo ohm. Somebody closes the switch. How long does it take for the current to reach half its maximum value? This is a classic RL circuit problem. Well, what is the maximum value for the current? We just saw it. E over R. Okay? So I need 1/2 E over R is equal to E over R times 1 minus E to the minus, I'm going to write it like this right now, minus R over LT. Yeah? That's half, this is max. This is 1/2 max. That's a weird X. 1/2 max. Cancel this. Doesn't matter. So I'm going to put the numbers in now. 0.5 is equal to 1 minus e to the minus 1,000 ohms divided by, I got to put this in henries, so 0.026 henries times t. I'll leave it like that. That's what I have to solve. How does one solve that? Put it in Wolfram Alpha and hope? No. Hope for the best. Well, we've got to move things around and take logarithms. Yeah. Well, let me go over here. What? Okay. So I'll move that to the other side. I get a negative 1/2. The negatives cancel. Right? So you get 0.5 is equal to e to the minus 1,000 ohms divided by 0.026 henries. I could put that as one number, and then that's T, right? All right. Huh? What happened? Oh, I got rid of the 1. Okay. Take the ln of both sides. You get the ln of 0.5. That's equal to minus 1,000 ohms divided by 0.026 henries. An ohm divided by henry is 1/seconds, by the way. Okay. T. ln of 0.5 is 0.693, I think.
Yes, but negative.
Okay. Yeah. Well, okay. Negative, yes. So you get, it's 0.69, is it 93?
Yes, it is.
Okay, times 0.026 henries divided by 1,000 ohms. That equals T. What do you get for that? Something in the microsecond range.
1.86 times 10 to the negative 5.
Okay. 18 microseconds. Okay. Are there questions on this? You should know how to solve these exponential equations. You all know logs of logarithms, right?